Lesson 5.5, roots and zeros. So we're talking about x-intercepts. How do you find x-intercepts in a polynomial equation? If you know what those x-intercepts are, how can you use that to make a graph? Right? So also some rules related to roots, zeros, x-intercepts, all the same idea. Got here the fundamental theorem of algebra says that the zero of a function f of x is any value c such that f of c is equal to zero. And so I got some axes to make you guys some examples here. What if you had y is equal to x to the power of 5? Or I'll use that as an example. Is yeah, that's it, right? So I know if I plug in 0 for x, 0 to the power of 5 is 0. So x is 0, y is 0. If I plug in 1 to the 5 is 5. If I plug in -1 to the 5 is -1. Okay. If I plug in 2 to the 5, see 2, 4, 8, 16, 32. The 32 is like way off the page. So it scoots way up here. And then if I plug in -2 to the 5, I get -32. So it looks it's sort of like a cubic, but it isn't. It's stretched way steeper. So x to the 5 over that. All right, what about if I have something like this? Like y equals x to the 5 plus dot dot dot. All right, and I'm cutting off a bunch of the polynomial. Maybe some x to the 4 minus some x to the 3 plus some x to the 2, something like that. Like what other kind of crazy shapes can you make out of this, right? Well, at most, like how many zeros could we get? We could get up to 5. Could go up, down, up, right? You could get something like that, right? In fact, if you saw a graph like this out in the wild, you'd say, well, this would best be modeled by a polynomial with degree 5. You'd have to start with the next to the fifth term because we got 1, 2, 3, 4, 5 places that crosses the x-axis right there. Okay? So this fundamental theorem of algebra says that I suppose this value is like, I don't know, like 3. I can say f of 3 is equal to 0. Boink. That's an x-intercept, so that'd be called a 0. That's all I'm saying. Right. And then let's say here, every polynomial equation with degree greater than 0 has at least one root in the set of complex numbers. Right. So we can see this here. Well, if I have x to the 5, I can have up to 5 roots. Right? I might not have all 5 roots here. Give you guys sort of a different perspective on this. What if I have y equals x to the 5 plus da da da, and it worked out a little different. So what if it went down, up, right? So something like that. So okay, well, let me count all the zeros. We got one here, one here, one here, and then well, actually that's it. Right? I mean, it does dip down here again, but it doesn't reach all the way to the x-axis. So it looks like I only have 3 zeros, right? Oh, now thing is though, let's see, am I getting ahead of myself? Oh yeah, almost. Let me read this list. Next bit. It says a polynomial with degree n, so degree 5 in this case, has exactly n roots in the set of complex numbers, including repeated roots. Right? So if I'm counting the roots, well, I only see 3 roots, but there's only 3 real roots. There would also be 2 imaginary roots. So it would add up to 5 because I have 1, 2, 3 real roots, and then maybe 2 imaginary roots with the I in it, which is square root of -1. That'd be true here. Here, with this one, I have all 5 roots are real roots because they all cross the x-axis. Over here, well, I only see 1, but this is the same thing as x times x times x times x times x, or if you like, you could say x minus 0 times x minus 0, so on. So however you think of it, it's the same root repeated 5 times, and that's what this multiplicity is. So repeated roots can also be called roots of multiplicity. Multiplicity is the number of times 0 is repeated in a polynomial. For example, f of x is x cubed is x times x times x. So the root 0 has multiplicity here. There it is. Right now you did it with 5, but it's the same idea. Okay, so these are interesting ideas. Descartes rule of signs. All right, here's a good one. So if you have some polynomial, here I'll just go straight to their example. So we got a polynomial here. We got the terms. We got x to the 5th, we got an x to the 4th term, x to the 3rd term, x squared, an x term, and a constant. Okay? It says the number of positive real zeros of that polynomial is the same as the number of changes in sign of the coefficients in the terms, right? Or less than this by an even number. Okay, so what does that mean? So look at their example here. So okay, I see this term is positive and then negative, negative, positive, negative, positive. Okay, so if you count how many sign changes there are, and they keep track of them down here, positive and negative, yes, that changes sign. Negative, negative, no, that stays the same. So I'm going to skip over that. Negative back to positive, boom, there's another sign change. Positive, negative, boom, there's another sign change. And negative back to positive, boom. So I'm looking at four sign changes, and they tabulate them up here. Got yes, no, yes, 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 yes. So I'm getting four. The book's getting four. So what that means is that there have to be four real zeros. Yeah, the number of positive real zero in the positive territory. So that's like to the right of the y-axis. So there would be four positive real zeros, right? Or possibly it says less by an even number. So if there aren't four, then there would be two. And if there aren't two, well, maybe somehow there is zero, right? But some version of that. There's either four, two, or zero. Okay. And then, okay, now that's only half of this. So what was the second half of the cartwheel sign say? Um, Says that the number of uh, negative real zeros is the same as the number of sign changes in the coefficients for p of negative x. So p of being like a polynomial function, right? Again, or less by an even number. Okay, so what does that mean? So let's pick up from the same polynomial example. What if we didn't look at f of x? What if we substituted in a negative x? Right, so they do that all the way down here at the bottom. We got instead of x to the fifth, they said, hey, let's plug in negative x to the fifth, right? Now, anything to an odd degree, the negative's going to come out, makes the whole coefficient, makes that whole term negative, right? But see, if you plug in a negative x in place of this x for x to the 4, well, anything to an even power, the negative cancels out, right? Because the negative times negative brings you back to positive. So it doesn't change at all. So if it was negative before, then that just doesn't change, right? And you go on down the line, replace this x with a negative x, replace this, and so on, all the way for every single term. Now, if you do that, which they did here, then again, all the odd powers, the sign flips, and all the even powers of x, it stays the same as it did before. So now let's count up the sign changes. So negative, negative, now that didn't change. Negative, positive, boom, there's one. And then positive, 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 and everything else is positive, so it never changes again. So that means there's probably one real zero that's to the left of the y-axis that's the same negative. Right? And it could be fewer by an even number, but I can't subtract two from one and still get a whole number. So right, so there's probably one. Oh, it says right here, there's one sign changes, so there is one negative real zero. Yeah, yeah. Right. But remember the positive case where we counted up four of these, there might be four or two or even zero positive real zeros. Okay, okay. So it's sort of a way to keep track of how many zeros could there potentially be. Okay, this kind of reminds me of, and it might be a good time to review anyway. If I go back just a few pages ago to 5.4. You guys remember rational zeros theorem? This is another way to hunt around for like, well, where should I kind of be looking for zeros? And we had this p over q method where we take the last term and the first term in the polynomial, right? Took the coefficients, took the factors of those coefficients, plus or minus, and divided them out. So I got 16 here and a 4 here. So like 16 over 1, 16 over 2, 16 over 4, right? And then 16 also breaks down into, has some factors too, like 8 and 4 and 2, right? And also 1, right? So you take each of those and divide by, so then they list out P, Q, again, these are all plus or minus, right? And so when you divide P by Q, you get, say, 2, 4, 6, 8, 10, 12, 14 places where you're looking for rational zeros, right? Now, they won't all be zeros, but there very well could be some in that list, and that would be a good place to start looking. Okay, so kind of reminds me of that. All right, so back here, finding zeros of polynomial functions. Right, yeah, I mean, that's kind of the point, what we're building up to, right? Like, where are these zeros for these polynomial functions? Right, so let A and B be real numbers, where, okay, b is not zero. Okay, a plus bi. So we're looking at a complex number, and if b is not zero, then yeah, it would have an imaginary component. This is a zero polynomial function with both coefficients. Then a minus bi is also zero. Interesting. So here's their example of what they just said. We got this polynomial f of x is x cubed minus x squared plus 3x plus 5. Okay. Now, let's say we did some work to find the zeros, and they found out one of the zeros is 1 plus 2i. Remember, I is the square root of negative 1. So this is a complex number. It has this imaginary component. Well, if that's true, if there's a 1 plus 2i, there must also be a 1 minus 2i. Huh. That's called the complex conjugates theorem. There you go. It's called the complex conjugates theorem. Okay. All right, let's do example 3 here. Use substitution to find zeros. Find all the zeros of this graph and sketch a rough graph. All right, so it's fine. So example 3 right here. We got f of x is x cubed plus x squared minus 7x minus 15. Right, so something like that. Okay, so we got to find all the zeros, right? And we have some tools in our toolkit here. Let's see, could I possibly factor by grouping? I don't see an immediate way to do that. Nothing where I would be looking for, are there any coefficients in these terms that are multiples of each other? Like if this was like 3 and 15, that'd be 1/5 ratio. And if this was like 2 and 10, ooh, there might be an opportunity there, but I don't see anything like that. Right. Um, I might look for, hey, I wonder how many potential zeros we could have, positive or negative. Well, let's look at sign changes. Let's apply this Descartes rule of signs. So I've got positive, positive, negative, negative. I see one sign change. So that means I should probably be looking for one real zero that's a positive value. And there would only be one, according to this Descartes rule of sign change. Okay? What if I plug in a negative value for x? Let me see what happened. So I'll put this in pinking so it kind of stands apart. So if I do negative x cubed plus negative x squared minus 7 times negative x and then minus 15. Okay, now let me clean that. So this is still up with negative x. So let's see what happened. So this term is negative. This term x squared is still positive. This square negative, it turns back positive. These two negatives cancel and gives you positive and then negative. Okay. So now let's look at the sign changes for not f of x, but f of negative x that I have here in pink. There's negative, positive, positive, negative. Ah, that's two sign changes. So that means there could be two real zeros in negative territory to the left of the y-axis, right? Or maybe there are zero, but there's either two or zero in the negative territory, and there's one in the positive territory, right? So I have an idea of how many zeros to look for. You know what else I remember too is if I go back, you guys remember rational zeros theorem? So I could take factors of 15, which would be 1, 3, 5, and 15, and divide by factors of 1, right? And then the plus or minus values of each of those. Okay? So here, I'll flip the page and let's see what your book suggests to do. Oh, they went with Descartes rule of signs right away, and they got exactly what I got. F of x, there's one sign change, so we're looking for one real zero in positive territory. And in f of negative x, there's two sign changes going from term to term, so we're looking for 2 or possibly 0. Oh, no. Look at this. They went with rational zeros theorem. Yeah, that's exactly what I was thinking. I was thinking, okay, factors of 15 over factors of 1, and then plus or minus. And I came up with the same list that I just verbally walked you guys through. So like P over Q. You guys remember that? P over Q? Right, so P could be plus or minus, and then factors of 15. So 1, 3, 5, and 15 itself. Right? And then Q is just, well, it's just a one coefficient here. So it could be plus or minus 1, right? Because it could be 1 times 1 or maybe 1 times negative 1. That's where I'm getting both those. And then if you do P over Q, right? So look at this. Let's do P divided by Q. Well, that would just be the same list as P. So plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15, right? So that's my list of where I want to start hunting around to try to find some x-intercepts. Like where are these zeros? So I'll make a table. Actually, you know what? I was going to start making a table, but your book did the same thing. Actually, yeah, I'll go ahead and draw it anyway, because this is what I was going to do, and it looks bigger on camera, I guess, if I draw it out. Okay. So what are some x values where I want to hunt around, and what are f of x? Okay. And I'll plug each of these into the calculator for this expression. Okay. So I have these 8 values, right? So I have -1, -3, -5, -15, and also positive 1, 3, 5, and 15. Right? So calculator time. Okay. Now I'm going to use that answer trick that I've been showing you. So everywhere I see X, I'm going to hit second answer. Okay, you guys see how I did that? I just hit second in this key and got it says answer. I'm treating that basically as X to the power of 3 plus X squared minus 7X minus 15. Okay. Now the first answer is junk. Don't worry about that. But if I plug in -1, okay, so now I'm starting to hunt around. -1, enter. Okay, now the calculator's saying something about -1. I scroll up, plug it in, bam. Okay, I get -8. -8. Right. I guess if you have your own graphing calculator, or if you want to utilize Desmos, that'd be okay too. But here's a way to do this scientific. Now I got this coordinate -1, -8. Okay, so did your book. Right? They have it in their x values in a different order than I do, but at least that number's consistent. And remember what I'm looking for. I'm looking for f of x to be 0. This is fundamental theorem of algebra. If one of these is 0, that would indicate an x-intercept. So let's go to -3. Plug that in and get -12. Okay, so that's not 0. Keep going. -5, -80. Okay, so that's not a 0. -15. Nah. Okay. All right, now we're getting really off, but all right. Let's look at the positive. Now, remember the negative territory? We were looking for there to either be 2 or 0, because it could be 2 or less by an even number, so 2 or 0, right? So maybe there's none, and that could very well be the case. Okay? How about if I plug in 1, I get -20. How about if I plug in 3? I get, there we go. There we go. That's it. Ding, 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 ding. Winner. Okay. And that's probably the only 0 because according to Descartes' rule of signs, I see one sign change in a polynomial, right? Positive, positive, negative, positive. And so it's right here from here to here. Okay. So that's probably the only one. I bet these other ones cannot be zeros. So if I plug in 5, yep, I get 100. That's definitely not 0. And 15, just to check my work. Yeah, 3,000 and something. Okay. All right. So did your book also get 3, 0? Yes, they did. Your book got the same thing. Okay. So that's probably the only 0. And if I want to make a graph, right? Well, there's some things I know about this graph, x-axis, y-axis. I know if I go over to 3, so the point 3 comma 0, there definitely is a coordinate here, and that would be a 0 in the function, right? I guess I could use long division, and I could factor x minus 3 out of this. Let me do that. I think it's a little extra. It's probably a little overkill, but it's probably good for practice anyway, do some long division. I wonder what would happen if I divide that out. X cubed plus x squared minus 7x minus 15. Just kind of curious. Anyway, so if this is 3, I'm going to factor out x minus 3, right? Yeah, let's just see what happens. Right, so x goes in x cubed, x squared times x is x cubed, x squared times -3 is -3x squared. Then subtract this off. So this minus this goes away. Okay, let me go ahead. I should have done this anyway. Just factor in a negative. Distribute the negative rather. Okay. All right, 4x squared, then drop down, -7x. Okay, now x goes into 4x squared, 4x times 4x squared, 4x -12x. Okay, subtract this off. So plus minus plus. So that gives me 5x. Drop down, -15. Oh, okay. Uh, x goes into 5x 5 times. Okay, so 5x, and then 5 times -3 is -15. Um, Yeah, actually, I shouldn't be surprised that there should be no remainder, of course, because x minus 3 was a perfect factor. We showed that right here, because it's got to be a 0. Right? So I think that this polynomial is the same thing as, and I'll write it right here, f of x. So this is the same f of x as we started with that I wrote in blue ink way back. Okay, has to be okay, x cubed plus x squared minus 7x minus 15. Sure, that works. But also x minus 3 times x squared plus 4x plus 5. Okay. Now, are there two numbers that multiply to 5 and add to 4? Nah, I don't think so. Right? I could use quadratic equation. Let me try a quadratic equation on this, okay, to try to factor this. So I'm just looking at this part right here saying, can I get some zeros out of this? Right? And they might be imaginary. So let's find out. X equals -b plus or minus the square root of b squared minus 4ac. You guys have done a lot of quadratic equation. And so I'm just naming it as and going along, filling it out. All divided by 2a. Okay. Right, so that would be -4 plus or minus, let's see, what is this? That's 16 minus 20. A square root of -4. Yeah, we're going to be getting some imaginary out of this. Okay. So -4. Now the square root of 4 is 2, but square root of -1 is I. So this is plus or minus 2i. That's whole thing divided by 2, right? Which is, this can also simplify. So -4 over 2 is -2. And then this simplifies to just I. where I, of course, is the square root of -1. Just to remind you guys that. Okay. Okay. So there's two more zeros. Right? It follows the complex conjugate theorem too, exactly like your book said it would. So it's -2 minus I and -2 plus I. Now, since those are imaginary values, that means that when I go to finish this graph, and I only have 1 point on my graph so far, that uh, there's going to be no other place the graph crosses the x-axis. This is it. This is the only one. Okay. Now, I do have a whole table of values right here. So I can sit here and I can plot all these points. Okay. Your book also gave you the graph right here, and they have the same coordinate ID right here at 3, 0. And I do see this is definitely a cubic, right? The graph comes back up, it goes back down. But just like I've been proving to you guys, it never again crosses the x-axis. Okay. Um, I guess if you plug in 0, you get -15. That's an easy point, right? So 0, -15. Okay. Here on, I'll just copy what the book has. So basically it does something roughly like this. Something kind of like that. Okay. I'm sure if I just plot all these points and poked around enough with it, that you get that. Or you can pop that in Desmos, right, if you want to go that way. But yeah, that's the graph. All right, pretty good. All right, example 4. Use a graph to write a polynomial function. Ooh. Yeah. So what if they give you a graph and you want to come up with an equation for it? Now, I did show you guys, sometime back, was it a week or two or three ago? You can plot points into Desmos and make a table in Desmos and create a regression curve, and it'll give you the best equation. Now here, I think I can probably construct this out of the zero. Like I see zeros at x equals -4, -2, and looks like +1. So I think if I multiply x minus -4, which also called, well, here, I'll go ahead and write that. X minus -4, x minus -2, and x minus 1. Okay. Let me throw one more idea. I'm going to slap in some value a in the front so that I can align exactly this y-intercept right here. So I can get that too. Yeah, let me see if I can also get this point. It looks like, here, I'll write it here, y-intercept at, and I'll write the whole coordinate. It's 0, comma, -8. Right? Okay, so if I plug in 0 for x, I should get -8 for y. Right? Well, I'm saying y. I could have said f of x, same idea. Right, so some stretch back, some vertical stretch factor, x plus 4, x plus 2, x minus 1. Okay. And I know if I plug in 0, I should get -8 out of this. Right. So therefore I can solve for a, and then I'll probably have the whole thing. Right. So 0 plus 4, 0 plus 2, 0 minus 1. Oh, actually, you know what? That worked out. Because look at this. 4 times 2 is 8, times -1 is -8. Okay. So what that means then is that a is equal to 1. Okay. So as an example, your book gave something to you guys that's real straightforward. The answer is just this right here. A is just 1. So the answer is just x plus 4, x plus 2, x minus 1. Now you could, of course, also distribute this out and create a full polynomial. See, did your book do that? Okay, they came up with the same factor expression I did, x plus 4, x plus 2, x minus 1. Okay. Yeah, they're suggesting that you go ahead and boil and distribute and everything. But okay, you create a full polynomial. Okay. All right. Uh, Example 5. A book publisher wants to release a special hardcover version of several Charles Dickens books. They know that if they charge $5 or $40, the profit will be 0 for each of. Okay. So we have a real world example. We're doing a profit example, which has been common throughout the book. Right? So kind of a business economics example, right? And they're telling us some zero values on a graph. Maybe if they charge $5, well, they're just barely covering the cost, and maybe most people are buying the books, but it doesn't really help them turn a profit here. If they charge $40, maybe there's so many people say, it's too expensive that they just barely recover their costs, and again, profit is 0. So they probably want to charge something in the middle, probably closer to like $20, where they get lots of customers, but they're also making a good profit. Right? So let's say graph polynomial function that could represent the company's profits in thousands of dollars, given the price they charge for a book. Okay. So I think, yeah, what I would want to do is have something like Profit, this is example 5. Right? Profit as a function of x could be something like, let's see, if I do x minus 5 times x minus 40, sort of the factored form like the example we just looked at. So if you plug in 5, this will come out to 0. Or if you plug in 40, this will come out to 0. Right? Now, the exact profit for anything in between, well, I'd have to know something else. They'd have to tell you more information because, like, what is this vertical stretch factor? Right? What are we looking at right in the middle there? All right, so I'm looking at the teacher's example off screen, and they didn't really address that. So, man, it's a little bit incomplete. Right, so they just didn't even put a vertical stretch factor at all. So I'll just go ahead and multiply this out. So it could be like x squared. So I'm doing FOIL, FOIL first. Here, you've got some FOIL lines like I normally do. First, outside, inside, last. Okay, you guys seen that a bunch. So x squared minus 40x minus 5x is minus 45x, and then negative 5 times negative 40 is positive 200. Okay. Oh, actually, you know what? One more thing. Actually, there is an interpretation on A, which is that A would have to be negative because like a reasonable price to charge would be something between $5 and $40, maybe closer to like $20 or something like that, right? Could make more sense. Um, if you take this equation at face value, see the problem with that is that there you have 5 here, you have 40 here. This is like x-axis is the dollars that you charge because profit, whatever, right? Is that it would look like this. But that would mean negative profit, which means you have to like either charge nothing or charge $1 million a book. Right? But that doesn't make sense. What would make a lot more sense is if you had some kind of profit curve that went like that. That would be more in line with what you guys are seeing. So I think A would have to be negative, and that's really as much as we know because they didn't give you any numbers other than that. So I could do this. I could slap on a negative to this whole thing. I could say the true profit as a function of price would be negative x squared plus 45x, 45x, and then minus 200. Okay, I'll just leave that at that because I guess the idea there. Yeah. All right, so let's jump into these book puzzles. I got some highlighted ahead of time. First section, solve each equation, state the number and type of roots. Right, so the number of roots could be 1, 2, 3, 4, 5, whatever. The type of roots could be either real or imaginary, I suppose. So let's do number 5. We got um, 4x squared minus 4x minus 1. That's equal to 0. Now, nicely, I do see this one's quadratic, so I could solve this with quadratic equation. I could do that. Do we see an immediate way to factor this? Maybe not easily. I'll go ahead and use quadratic. Okay, let's go. Quadratic equation with this one. So I'll say x equals negative b. So that's positive 4 because negative is negative 4, positive. Plus or minus the square root of b squared minus 4ac all divided by 2a. We get quadratic right there. Okay. So let's just clean this up. So 4 plus or minus. Now this right here is 16. And then two negatives cancel. This is another 16. So this would be square root of 32. This whole thing divided by 8 is what we got. Now 32, that's 32 is the same thing as 2 times 2 times 2 times 2 times 2, right? So 2, 2, 2, 2, 2, right? Now, anytime you have a bunch of numbers multiplied underneath a radical, if you find a pair of numbers, you can pull that out. Like the square root of 2 times 2 is just 2, square root of 4 is 2, right? Right. That shows a pair. It also shows a pair. So this is the same thing as 4 plus or minus. All right, this is 2, this is 2, that makes this 4, and I still have this 2 underneath the radical. Right, so that stays there. It's all divided by 8. Right, and then finally I can simplify. So 4 over 8 is half, and then plus or minus root 2 over 2. Looks like that. Okay. So that should be, yeah, I'm looking at the teacher's guide off screen. They got exactly the same thing I got. Okay. So there are 2 real roots. Okay. Now, they'll be irrational because the square root of 2, it's a non-repeating decimal, goes on forever. Okay. But there's nothing imaginary. There's no i's, there's no square roots and negatives, nothing like that. All right, so we got two real roots on that. Okay. You could use that to graph the problem or not. Okay. Actually, here, let me go ahead and do that. I'm going to pause this video, pop that into Desmo so you guys can see exactly also what that looks like. And there you go. Yeah, those numbers look about right. I'm sure if I popped in that whole square root expression in my calculator, I'd get probably those two right there. Yeah, that looks about it. Yeah, got a parabola. Looks good. Looks good. All right, next one. Number 6. Like, oh yeah, I thought this one looked kind of exciting. We got x to the fifth minus 81x. Okay. Now these are all equal to 0. You guys notice that these are all equal to 0 all the way down? Otherwise, I'm always tempted to do y equals or f of x equals. Okay. That equals 0. And so I have two terms. I do see that both of them have an x in them, so I'll go ahead and take an x out. That gives me x to the fourth minus 81. Okay. And okay, so still equal to 0. We're trying to figure out where does this cross the x-axis? Hence equals 0. Ah, do you see 81? It's 81. Isn't that, let's see, I think that's 3 times itself a bunch of times. Yeah, that's 3 to the power of 4. Huh. Right. And this is x to the power of 4. We have a difference of powers of 4. Interesting. I'm sure there's a way to factor that. Right. What if I do this? What if I do x squared minus 9 and x squared plus 9? I think that should work, right? Okay, so this x takes that x, that's fine. Right? Let me try FOIL and see if it works back here. So x squared is x to the 4. Yep. Outside, inside cancel. So there's no x squared term. And then negative 9 times 9 is it negative 81. Yeah. So it totally breaks down like this. And here I have a difference of squares. And here I have a sum of squares, which won't give me real zeros, but will give me imaginary zeros. Okay? So I got this x out here. X squared minus 9 breaks down into x plus 3x minus 3. Now, x squared plus 9, be careful about this one. This does factor, but only in the imaginary world. So it'd be x plus 3i, x minus 3i. Okay, so remind you guys why that's true. Right? So here, I'll prove it backwards. So x times x, I'm doing a FOIL right here. X is x squared. Bing. At the outside inside do cancel. So negative 3ix, that cancels. Okay. And then 3i times negative 3i. Well, 3 times negative 3 is negative 9. But I times I is negative 1. So the negative cancels and it brings you back to positive 9. Yeah, so that's exactly how that factors. Okay. Now that I have this in fully factored form, I see what all the zeros are. So there's zeros at x equals, here, I'll put it in curly bracket form, okay? So 0 from this one, because if I plug in 0 here, the whole thing zeros. I got negative 3 right here. I have positive 3 right here, because 3 minus 3 is 0, okay? And then here I have a couple of imaginary solutions. So there's negative 3i and also positive 3i, okay? And that would be 5 zeros, okay? Now, your book was saying before that if you have x to the power of 5, since it's degree 5, there should be 5 zeros. They won't necessarily all be real. In this case, there's 3 real zeros and 2 imaginary. Yeah. But the total number of zeros, in this case 3 plus 2, does add up to 5, just like your book promised. Yeah. Actually, what were they calling that? Where it would add up to that was a complex conjugate. It was a I think the corollary to the fundamental theorem of algebra. Yeah, it's way back on the first page. Okay, so let's go. Next one. Number 15. Got, x to the power of 5 minus 8x to the power of 3 plus 16x. This is all equal to 0. Okay? So now I have 3 terms. I do see right away they all have an x in common, so I'll go ahead and take an x out. X, and then that leaves me with x to the 4 minus 8x squared plus 16. Okay. Now, this, I think I can't factor that, right? Think I can factor that? So, like, what are 2 numbers that multiply to 16 and add to negative 8? I think it's negative 4, isn't it? So it'd be like something minus 4, something minus 4. But that something isn't x, it's actually x squared. Let's watch this. X squared minus 4, x squared minus 4. Like that would have to fit, right? Because watch, if I FOIL and go backwards and prove this works. X squared is x to the 4. Bing. Negative 4 squared, negative 4 squared is negative 8x squared. Negative 4 times negative 4 is positive 16. Yeah, it totally factors like that. Now, I have difference of squares here, difference of squares here. So this is really x plus 2, x minus 2. And then this one, same idea, x plus 2, x minus 2. That is as fully factored as you can get it, fully factored form. Okay. And this one, so I have zeros, and they're all real zeros. They're all real zeros at x equals, well, 0 from this one, -2 from here, and +2 from here. Okay. Okay. Now you might say, well, there's only 3 real zeros. The degree was 5. Well, shouldn't I have 5? Right? But some of these have multiplicity too. Like this one shows up twice, and this one shows up twice. What that means on a graph is that it's just going to come down and like just touch the graph, but not actually cross it. Here, I will make a prediction exactly what this graph looks like, and then I will pull this up on Desmos and show you guys that. Well, it should be the same thing as what I'm about to graph. I don't know. I haven't actually put this in Desmos yet, but there should be. Actually, let's make this a little bigger. Um, let's go -1, -2, and +1, +2. Ignore that straight mark. -1, -2, 1, 2. Okay. So at -2, there's a 0 with multiplicity 2 because it shows up twice. Okay. So there's definitely a 0 here. Okay. There's also a 0 at +2, but also multiplicity 2. Okay. So also, okay, and then there's of course a 0 at 0. Okay. Now let me think about in behavior to get this graph exactly right. I see what's going to dominate is this x to the fifth term, and since it has a positive leading coefficient, in this case +1, I know if x gets really big, y gets really big, it's going to go up and to the right. The whole graph goes up and to the right. And what if I go to the left? So if I plug in a huge negative number to an odd power, it's going to go hugely negative, which should be down to the left. Okay. So put it all together. I think it has to look like this. It has to go like this. Okay. And then multiplicity 2 means it just boink, just touches the x-axis and turns around. Okay. Now, I see it's going to cross through this one because multiplicity 1, so it crosses through. Okay. And it comes down and just touches this one, boop, and then on its way it goes. Okay. So I'm pretty sure the graph should look like that. Here, let's throw that in Desmos here. Yeah, would you look at that? It's exactly what I said it was going to be. Yeah, that's the same thing I just drew. Yeah, same thing. Same thing, same thing. All right, we are good. All right. How about this? I should review one of the concepts we did, or use this as an example. Was it, you guys remember Descartes rule of signs? We covered that earlier. Right. So if you look at the number of sign changes, that tells you the predicted number of positive zeros, and then if you plug in -x for x, that predicts how many negative zeros you get. Right. So how many sign changes do I see straight up on the polynomial? Well, we got let's see, positive, positive. I wonder if the fact that one of these is 0, if that messes this up. Huh. Yeah. Actually, let's think about that one. Here, let's go on to next one. Number 19. All right, so this section, we're going to state the possible number of positive real zeros, negative real zeros, and imaginary zeros for each function. Yeah, this sounds like Descartes' rule of zeros. Okay, so let's try this out. Number 19. Here, and I'll write this function bigger so it's easier to see on the camera. We've got f of x is x to the power of 3 minus 8x squared plus 2x minus 4. Okay? Now, how many sign changes do I see? Well, there's positive to negative, so bam, there's 1. Negative back to positive, bam, there's 2. And positive back to negative, bam, there's 3. So there could be 3 or, and then you start subtracting off 2 at a time. So I'll say 3 or 1 positive real zeros. They did say real, yeah, they did specify real zeros. Okay? And then if I want to get the negative real zeros, I have to plug in negative x over c and x. Okay, so I'll go negative x to the power 3 minus 8, and then negative x being squared, and then 2 negative x, right, and we got this -4 at the end. Okay. Now I definitely have to clean this up so I see what's going on. So -2 in odd power is overall negative. Negative, negative, negative makes a negative. Okay. But if you have a negative that's being squared, that turns back positive, okay, which means that this original negative sign just stays as it was. Okay, and then this negative comes out in front, and then negative. Right. You can see how all the terms are negative, 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 negative. Okay. That means there's zero sign changes. Zero sign changes. Okay. Which means zero, negative, real zeros. Okay. So it should be like that. Okay. Check the okay. Zero. Okay. Okay. One more detail. So I'm looking at the teacher's edition off screen. They got this, yes, check. They got this, yes, check. But there's one more detail in the premise. See, it says how many imaginary zeros are there? How many imaginary? Right. Well, the degree is three. Right. We have some kind of cubic going on, which means there have to be three zeros altogether. Right. Now, they might all be positive real zeros. That's possible. We might have one, two, three real zeros, and that's it. And they're all real. They're all positive. Right. We know we're not getting anything on the negative side, right? So that's out of the question. Okay. But there might only be one real zero. And if that's true, then where would the other two zeros be? Well, they'd have to be imaginary. So there could be either zero or possibly two imaginary, or you could say complex zeros. Wait, did they call them imaginary or complex? Yeah, they said that imaginary. Okay, so same idea, right? Right. All right, I'm going to pause this video, pop that into Desmos because I'm curious to see what that graph actually looks like. Okay, I just plugged that in right there. You see, that's the same thing. Yeah, interesting. Okay, so yep, it's definitely a cubic, goes up, down, and then back up. It looks like there's only one real zero. It's right there. Bam, right there. Okay. And well, there could potentially have been other ones. Like if I didn't do -4, what if I did like +5 or something? See how it can scoot way up and you can actually get more out of that, right? That's not what it said, so I'll just go back how it was. Right. Yeah, so there would be two imaginary zeros, and you can see that from the graph. Yeah, there's one real zero right there. Bam. And then, well, the other two have to be imaginary. Yeah, 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 yeah. So that is it. Okay. Right, so according to the rules we followed, we're looking for all right, three or one of those, none of those, and zero or two of those. And then we saw on Desmos the actual answer, which is that there's only one of those, and the other two have to be imaginary. So like that. All right. So we are looking number 21. All right, so same premise, different equation. Let's see a different example here. We got q of x is x to the power of 4 plus 7x squared plus 3x and then -9. Right? Now I know anything to an even, like if you have an even degree, right, it's the end behavior is going to do this. Right? If you have a positive leading coefficient, it's going to do something like this. Now, does it go down and then kind of back up, or does it go down, up, to make like a W looking shape? Right? I don't know. It's one of those. Okay. Okay. I'll just run backwards. I'll plug this into Desmos first, so we know exactly what we're looking at. And so Desmos. All right, bam. Okay, I think that's that expression. Okay, that looks like that. All right, let's see what does this graph actually look like. All right. Okay, okay. So yeah, it looks like it goes down and then back up. Sometimes to power 4 it just does that. Right. This is not a parabola, although at a glance see my thing. Oh, it's not a parabola? Is it? It actually isn't. But, okay, it looks like there's going to be one negative real zero and one positive real zero. Okay, so that's the answer because you're looking at the answer right there. Okay, so again, I want to do one a little backwards from the previous one, right? So you can see this from a little different perspective. So we know there's going to be two real zeros, one that's negative and one that's positive. So let's use Descartes rule of signs. Descartes rule of signs. I think that's what it's called, right? Descartes, yeah, Descartes rule of signs. Got a little apostrophe right there. Right, so this is a positive term, positive, positive, negative. Okay, so there's only one sign change is between these last two terms. That means, therefore, we should be looking for one real zero that's positive. Well, one real uh, okay, positive zero. Okay, which you guys saw on the Desmos graph anyway, that there was one real positive zero. Okay, so that's consistent with the graph you guys just saw. Okay, now how about negative real zeros? I can find by doing q of negative x. So that's negative x to the power of 4 plus 7 times negative x being squared plus 3 times negative x and then -9. So okay, power of 4 is just plain x to the 4. this positive stays positive because 7x squared. Right? Notice we actually skipped over an x to the 3 term, so there is no x to the 3. Right? Now here, x to the 1, this negative is going to come out, and there's a sign change. Right? And then it's minus 9. Right? Now let's hunt for from term to term. Right? So uh, positive, right? Stays the same. Positive to negative. Bam, right there. Ding. Right, and then negative. Okay, so nothing from there. But from this one right here, we're looking for one real negative 0 from there. Right. So one positive real 0, one negative real 0, right, which is exactly what you saw in the graph. Okay. Now there's one more detail, which is that the degree here was 4. So there should be 4 zeros. Well, I'm only seeing 2. Because the other two have to be imaginary. Let me make sure it's, yeah, okay. And just check the teacher's edition. It says the same thing, right? And also there's 2 imaginary zeros. Right, there you go. And that's the full answer. Right, one real positive, one real negative, and 2 imaginary. That brings you up to 4. Yeah, yeah. Doing good, doing good. Number 31. Find all the zeros of each function and use them to sketch a rough graph. Oh, okay. All right. So 31. We got h of x is x to the power of 3 plus 4x squared plus x minus 6. Okay. Now, do I see how this can easily factor? Uh, okay. Or like factor by grouping or anything? I don't know. Nothing really jumps out at me. Okay? But I do remember the rational zeros theorem. Okay, I'll spell it out. Rational zeros theorem. Okay. So we can do factors of 6 over factors of 1. So P could be plus or minus 1, 2, 3, 6. And my Q is, well, just plus or minus 1. Okay. So take each of these 8 values, because 2, 4, 6, 8, because plus or minus, divided by 1. So it's going to give me 8 numbers I can start hunting around. Okay. So I'm going to make a table. And I have some pretty good options to start looking for rational zeros. So x and I guess h of x. Okay. So let's go. Here, maybe I'll put them in order. -6, -3, -2, -1, 1, 2, 3, 6. Okay. So I hope I get a bunch of zeros out of this. Let's see. I mean, if I get 3 zeros, that would be all of them. I mean, I could just stop there if I get 3, because I know there's 3 zeros altogether. I just don't know at this point if some of these are imaginary or not. So let's do answer to the power of 3 plus 4 answer squared plus answer minus 6. Okay, so you guys know answer stands for x. I just modeled this expression. Okay, now let's plug in -6. So -6, enter. Okay, so the calculator's thinking -6. Plug that in. -84. Okay, well, that's not 0, so that's not what I'm looking for. Let's try -3. Oh, I got one. I got one. Ding, 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 ding. Winner. Oh, yeah. Let's try -2. Oh, 2 in a row. Oh, I wasn't expecting that. Oh, yeah. Ding, 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 ding. Double winner. Oh, yeah. You're on a winning streak. -1. Okay. Didn't quite work. -4. Let's try pause one. I'm really looking for one more 0. Oh, there it is. There it is. Ding, 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 ding. Okay. Now, since that's 3 zeros and the degree was 3, and almost certainly exhausted the list. I mean, there's no way these other ones could work. And just to confirm that, I'll go ahead and plug those in. Yeah, so 220 is a coordinate, 360 is a coordinate, and 360 is a coordinate. Okay, which none of those were going to come out 0 anyway, but I just wanted to confirm that for you guys. All right, so we got to make a graph out of this. Well, I know where the zeros are, so that's a great way to start. And I also know the in behavior because a cubic, this is a cubic with a positive leading coefficient. So it's probably going to go like up, down, up, and go up and to the right forever and down to the left forever. Okay, so that could be really helpful also. All right, let's get x-axis, y-axis. Yeah. Let's go -1, -2, -3, and then +1 here. Okay. So I know some coordinates. And if I plug in -3, I get 0. If I plug in -2, I get 0. If I plug in 1, I get 0. And then the overall graph shape is just going to go up, down, up. Now, what that would also mean is it crosses the y-axis somewhere here in negative territory. I'm kind of curious where that would be. Actually, we can see it right away. Because if you plug in 0 for x, here, I'll add that to my table right here. I'll squeeze it right at the bottom. If I plug in 0 for x, 0, 0, 0, minus 6, that would give me negative 6. Yeah, wouldn't it have to? If you plug in 0 for x, you get negative 6. So I'll put negative 6 right about here. Right? And that would have to be the y-intercept. And so overall, this graph's got to look basically like this. Bam. Right? That should be pretty close. Right? And of course, we have a bunch of other points too. But I could plug in like 220 if I wanted to. I guess -1, -4 is a point. I see that right here. Okay. All right. Okay. I'm going to switch over and pop this in Desmos and confirm that that is, in fact, the graph. Yeah. And look at that. That's pretty much what I drew, isn't it? Yeah. Right. Let's see. If I made it any better, it looks like. Well, actually, no, that is pretty much what I drew. Yeah. Yeah. All right there. Boom, boom. It's about the same thing. All right. So we are good. We are good. All right. And then, all right, one more I'll do with you guys. Number 42. Write a polynomial that could be represented by this graph. Okay. All right. So I see that there are x-intercepts, also called zeros, at x equals, I'll have a list here. So -2, +1, and +3. Okay. There's also a y-intercept at y equals 6. So 0, 6 is a point. Okay, so with all that in mind, I'm going to say f of x, or g of x, or h of x, or y, whatever you like, right, is, I'll write this in factored form. So it'd be x minus -2, or x plus 2, if you like, x minus 1, and x minus 3. And then I'll slap on some coefficient I'll call a on the front, because I do want to align this y-intercept. So this will eventually come out to whatever, however, right? And then I can solve for a. So I know if I plug in 0, that this whole thing has to be equal to 6. That's what a y-intercept of 6 means. All right, so let's go ahead and solve for a. What is a equal to? So 0 plus 2, 0 minus 1, 0 minus 3. Okay, well, 2 times -1 is -2, times -3 is 6. Oh, it is 6. Yeah, look at that. What that means is that a is very simply equal to 1. Right, so your book gave you probably the easiest version of that it could have. Yeah, so that's nice. Right. So the answer could just be f of x is, now in factored form, it would be x plus 2, x minus 1, x minus 3. In fact, if Alex asked you this exact question, I bet they would take that factored form and you'd be good to go. Okay? If they ask for standard form, but let's do that just to close out this bit. Since this is the last example I'm doing, I'll go ahead and FOIL first, outside, inside, last. Later on, I'll distribute this piece. So I'll put this in standard form. So we got x squared minus x plus 2x. That's overall plus x. And then minus 2, because 2 times -1. Okay. Now that's all multiplied by x minus 3. So let's do a super distribution here. So I need to multiply each of these terms by each of these terms. And so like 6 ways here. Okay. So f of x equals, okay, I got x to the power of 3 from x squared times x is x to the 3. We got minus 3x squared. We got plus x squared. And then minus 3x. And then minus 2x. And -2 times -3 is positive 6. Okay. Okay, so this expanded form, and I can do one more thing here. I should be able to clean up some of these. Like I have a couple of x squared terms I can group together, and a couple of x terms I can put together. Okay, so the standard form of this function is going to be x to the power of 3. This overall looks like minus 2x squared. This would be -5x, and then plus 6. That's referred to. Okay. Okay, look at the teacher's edition. They got exactly the same thing. All right. Because the teacher's edition look at did actually list this in standard form, which is that right there. Okay. So this function, are the same function, both the same function. And if you graphed it, it would be this graph right here. All right, boom. That is a wrap on 5-5.